see right up in there. Beds that are just maybe a centimeter thick and pretty much planar. In the modern world, if you go to a desert and look at sand dune deposition, what you see on the sides of the sand dunes are little sand ripples, wind ripples. And as the wind ripples move across the surface of the dune, they leave behind a thin little layer. And that's what this stuff is. It's called translatant stratification, made by the movement of wind ripples across the side of a great big sand dune.
It's a little hard to visualize. Yeah, something like that. But when you say translation, what's going on?
What's happening is that the wind ripples are migrating, and as they migrate, they leave a thin layer of sand. Okay, and so that's your layer. That's one. Then another wind ripple comes by an hour later and leaves another layer and another. If you've been out in a desert or coastal dunes when the wind is blowing, you know those little sand ripples move along at a pretty good speed. And so that kind of what's called translatant stratification is produced on the sides of big dunes by the movement of little wind ripples. This kind of stratification is not very common in water-laid dunes. If you look at water ripples, they're usually bigger than wind ripples. They usually make little scours. They make an irregular surface. They make a thicker layer. You don't have this very even, planar, almost pinstripe appearance of the rocks in underwater dunes that you do in aeolian dunes, in air dunes. So we think, we believe, and I say we, I mean Professor Dodd and myself, we think that this part of the St. Peter sandstone was deposited on the edge of a cratonic dome during a time of low sea level, and the sand was being moved by the wind. The St. Peter sandstone sits on top of a huge unconformity. You know what an unconformity is? A big break in deposition. Around here, the break in deposition was about 20 million years long. It was a monster unconformity. This is one of Larry Schloss's big craton-wide unconformities. The Tippecanoe unconformity, he called it. And on top of that erosion surface is deposited this aeolian sand, which makes sense. It was above sea level. Sand was blowing around. It accumulated on that surface.
So, can you say, is this younger than the St. Peter in Nebraska?
Dating the St. Peter is an exercise in great futility because there aren't any fossils in it, or hardly ever.
Then how do you know it's all St. Peter?
That's, well, St. Peter, the age of a formation has no bearing on the definition of the formation proper. So formations can transgress time, as we all know. In fact, I think you're right. This sand blanket is probably of different ages in different places. And while Wisconsin had its head out of the water, the Michigan basin was still subsiding and was wet most of the time. So the St. Peter sandstone in the Michigan basin, as seen in a core, will be full of burrows and cross-bedding about this big. It was clearly aqueous while we were up on the edge of the dome. The sand was blowing around up here. So the St. Peter sandstone as a sand blanket probably represents a number of different sedimentary environments. all of them utilizing this pure sandstone that had been derived from the cratonic interior, recycled from previous sandstone formations during that 20 million year sea level drawdown. Up in the Twin Cities, part of the St. Peter was also aqueous, and there are actually fossils to be found in the rock, and they were Middle Ordovician age, just the way they would be. And so we know it's more or less the same equivalent as like the Platteville Formation, which immediately overlies it. But getting a fossil out of this stuff, out of pure sand, bad enough in the first place, Aeolian, before there was any land life,
Not even amalgamate.
No. No, and certainly no pollens or anything like that, as far as we can tell. Okay, eventually, the sea level came back up. Eventually, a transgression occurred. And eventually, this dune field got drowned. And you can see that drowning event in this outcrop. And that's what we're going to do next. We're going to walk up the hill, and you're going to tell me when this big scale planar bedding disappears, and instead you see smaller scale little trough cross beds, which would be indicative of the surf zone coming in and tearing up the big dunes. You're going to find that for me, and then we'll recongregate.
There's something troubling about the pattern of the weathering of the outcrop. I mean, I don't see a lot of these humongous crossbeds like I see at Zion.
Yeah. Part of the problem is the outcrop isn't big enough. We've got an outcrop down near the Illinois line where you can see an actual, well, it was on that 83 trip. I'm sure you recall exactly.
Yes, in fact, I got the sample from
There's like a 30 or 40 foot cross set that's visible because the highway department went right through this ancient dune. Here, you don't see very much. You just see little bits of what were, I think, much larger cross sets. I'll say one more thing. There's a special kind of structure called adhesion ripples. Adhesion ripples. They're formed by sand blowing across a damp surface. You can see them at the beach. If you go out to the beach and the wind is blowing, but the sand is still wet from the tide going out, you can see the sand sticking onto that surface by capillary action. And it'll form little lumpy ridges. Those are called adhesion ripples. In most cases, they dry out and blow away. But every once in a while, one of these things, it's just a few centimeters thick usually, they'll get buried. And then they can be preserved in the rock record. You can see them forming today. You can see them in ancient Aeolian sandstones like the Navajo. And you can see them in the St. Peter. And that's what finally convinced us that we were dealing with an Aeolian sediment here, was when we found the adhesions in the St. Peter. Right here near Madison. Adhesion ripples can't form underwater. They can only form by wind-blown sand sticking onto a wet surface by capillary action. Underwater, you can't have any capillary action. You can't make any adhesion ripples. So the adhesion ripples, which I've never seen at this outcrop, so don't ask, but we've seen them at a number of places around here. Those adhesion ripples also say to us Aeolian deposition. Questions? Okay, take a look at a piece of the sandstone with your hand lens. Make sure you can see the little beautifully rounded quartz grain, rounded by the wind action. And then we will start slowly walking uphill. Stop when you get to the transgression.
Oh, they're beautiful, and they're frosted.
Yeah.
Is frosting conclusively indicative of
Yeah, well, it's I wouldn't say conclusive, indicative, yeah. But the rounding is very impressive.